Model Land is a wonderful place. In Model Land, because all of our assumptions are true, we can really make progress on understanding our models and how they work. We can make predictions, we can investigate many different configurations of a model, and run it with different inputs to see what would happen in different circumstances. We can check whether varying some characteristics of the model would make a large or a small difference to the outcomes. The assumptions that underlie our statistical methods are also true in Model Land, and so our statistical analyses can be unencumbered by caveats. That's not to say life is easy in Model Land. We still have to make the model and do the math. Whole careers can be spent in Model Land doing difficult and exciting things. Model Land is not necessarily a deterministic place where everything is known. In Model Land, there can still be uncertainty about model outcomes. The uncertainty might arise from our limited ability to measure quantities or initial conditions, or from difficulties in defining model parameters, from randomly determined elements in the model itself, or from the chaotic divergence of model trajectories, also known as the butterfly effect. In Model Land, these uncertainties are quantifiable, or at least they are quantifiable in principle, if one had a sufficiently large computer. With a smaller computer, we can estimate the uncertainties and, given further information, the estimates we make will converge on the right answer. In the gap between Model Land and the real world lie unquantifiable uncertainties. Is this model structurally correct? Have I taken account of all relevant variables? Am I influencing the system by measuring and predicting it? Most fields distinguish between these two kinds of uncertainty. In economics, the quantifiable uncertainties are often referred to as risk, and the unquantifiable as uncertainty. In physics, confusingly, the exact opposite terminology is sometimes used, and uncertainty generally refers to something that can be quantified. Unquantifiable uncertainties are variously known as deep uncertainty, radical uncertainty, and epistemic uncertainty. Let's stay in Model Land for now. Think of a billiards table and the uncertainty involved in predicting where a ball will end up when you hit it. In principle, this is a simple calculation involving energy, friction, and deceleration along a straight line. In practice, though, even in Model Land, we can recognize the limitations of a single calculation. There is a measurement uncertainty because you cannot define exactly where the ball is to start with. There is an initial condition uncertainty because you cannot define exactly how much energy you will impart to the ball when you hit it. There is a boundary condition uncertainty because you cannot define exactly how much energy the ball will lose when bouncing off the edges. And these, taken together, result in a random uncertainty about the exact position of the ball when it comes to rest. In principle, you could define a range of plausible conditions for each of these quantifiable unknowns and use them to calculate a range of plausible resting points for the ball after the shot. With luck, when the experiment is tried, the ball would be somewhere near the middle of that range. Physicists would refer to the plausible range as the error bars of the calculation. Statisticians might call it a confidence interval. Deep or radical uncertainty enters the scene in the form of the unquantifiable unknowns, things we left out of the calculation that we simply could not have anticipated. Maybe it turns out that the billiards table was actually not a level surface. Your opponent was blowing the ball off course, or the ball fell into a pocket rather than bouncing off the edge. In that case, your carefully defined statistical range of projected outcomes could turn out to be completely inadequate. These are also called epistemic uncertainties, from the Greek episteme, knowledge, because they reflect the limits of our knowledge and the limits of our ability to predict.